Okay. Can you see my screen? Can you listen to me? Okay, thank you. Oh, I forgot to set the time, huh? So maybe we'll stop at the 350 lah, huh? 350 and then rest. And, 350 ah? 345. 345, then we stop for 10 minutes, then continue again until 4:30. Okay, where are we now? Okay, so the last lecture we talked about is a general motto lah, nah? So let me know if let's say my voice is too low, huh? Okay, DC motor is not in our topic lah, but I need to bring you to the DC motor first, so that you can we go from the easy one and then we'll go to the more complicated, nah? So DC motor, we have a wound field, we are separately excited, shunt excited, compound excited. This one is I think you already gone through during 306 which is an electro machine in the lab. I think you have learned about what is the separately excited, how the connection, how the shunt excited works. Then okay, but this one is I just want to let you know there are the field types of the DC motor with a wound field. Wound field means it has a coil. For example, it has a coil like this. Then here also have some coils. No, so that one is called wound field lah. Maybe I show you the later on lah. Maybe I show you the video first. Wait, let me stop presentation first. Show you a video. Where's the video? Video. DC motor. Yeah, I think this one. Maybe I need to open this and try. And test this one. Okay.
And DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor.
This is one of the DC motor lah. We can see that this one is the wound. Then wound field. This one is the stator field. Is it? Yes. Then this is the fan. No? So when we learn about the heating and cooling, right? This one is called air force. Air force. Then this is shaft. This is the commutator. This is the carbon brush. It's like the 2D pencil, carbon. Then we have a bearing, shaft, stator. The part which do not rotate is called stator. The part rotate is called rotor.
Let's first start with the simplest DC motor possible. It looks like this.
This is the simplest.
The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate.
Okay, so this is the basic of the magnetic circuit, where we learn about Fleming left-hand rules and Fleming right-hand rules. For the Fleming, if let's say we want to generate kinematic rotation, that is a force. So how to get the force is use a Fleming left-hand rule. So you can see that we have a three conditions. One is it must be a conductor. Another one with a current. Then another one, it must have a field. So if let's say we use the left hand, we point our second fingers towards the screen. That's the current of our left hand side. Go inside, and then the yellow field is our middle finger. Right or not? Eh, sorry. The second fingers is point to the south, because the field is point to our right side, and then the current is go inside. So the middle fingers we will point into the screen, which is the current, the blue color current, and then the red color will be our thumb. It shows the force. Same as well on the right side. So this is the we call current carrying conductor. The conductor that carry the current then generate force. Nah? Current carrying conductor, which means the conductor that carry the current.
You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources. To know more about it, please check the next video. Thank you.
Okay, so this is the so-called the DC operation of the DC motor lah, nah. The listen of. Sorry, tersalah tekan. Oh, still recording ah. I'm sorry ah. Just now, have you finished watching the video or not? Huh? Hello? Have you finished watching the video or not? The operation of the DC motor?
Yes, finished already.
Finish already ah. Okay. Sorry. Just now tersalah tekan my Windows. Okay, so we can see that if let's say we cut the cross sectional, which means we cut it and then put it into 2D, it become like this. So the rotating part is here. Then the static part here. So this is our stator. This is our rotor. Okay, then we call wound because wound is a past tense of a wind. Wind. We wind it. Wind like this. Wind like this. That's why it's called wound. But why we call wound field? Because the field created is by the winding. The field is the field that need to create through here and then go back to here. Is created by the winding. So we call wound field lah. So what is armature winding? Okay, armature winding is we have a lot of windings. Sometimes we say, hey, doctor, what is the excitation winding? Doctor, what is the armature winding? So excitation winding is the one who excite and create a field to interact with our stator. That one is called excitation. For example, we create, where is in DC motor, where is the armature winding? I think this is the excitation winding. This one is excitation winding. Armature winding is it's the winding that we inject the current so that the motor can run one. It's not to excite it so that interact with the armature. No. So this one is armature winding. This one is armature. Inside is excitation. Excitation is something like we want to make it interact between two fields so that it can make some movement. Then we have a commutator. This is a commutator. Brushes. This black one is brushes. Fast dynamic response, easy to control field current or armature current. From many years, 1930s to 1980s, the wound field DC motor have supremacy over AC motor. Disadvantages is gear, tear, and sparking. Okay, in the brushes, this brush with a commutator always has sparking. It's so-called a sparking. And then the wound field could also be replaced by the permanent magnet. Okay. So sometimes, if let's say we don't want to use a DC motor, we can just use a magnet. This one. This one is magnet. Oh, so if let's say this one is magnet, means this one is excitation. Sorry. Then this one will be armature. Yeah, because it's used to excite and interact with the rotor part. Huh? So sorry, I give you the bullet information. This is the brush, carbon brush. Okay, so another type is the classical AC induction motor. Stator to carry the polyphase winding. Polyphase maksudnya it can be one phase, no, single phase. It can be two phase, three phase, five phase, seven, six, macam ni boleh. Rotor could be squirrel cage or wound rotor type. Wound rotor type means the rotor is wound like this. Then squirrel cage one, it will be like this. This is squirrel cage, no winding inside. And then rotor setup, rotor magnetic field through the induction process from the main field. Then we have a slip. Power factor is always less than 1. This one is they have is all the operating condition we call double revolving theory inside lah. So I hope that you already understand when you took the subject of 306, the basic electrical machine, and I will not repeat here for the induction motor. And then yeah, it is the most cheapest motor lah, because manufacturing is quite easy. They use the so-called the cast, we call sand casting. This process is called sand casting. So for example, we put a lamination stack, and then we do some the mold, M-O-U-L-D. Okay, then we'll press it, and then there's aluminum, right? Then it will go into here, then make the all the fill up the kosongan. Then we take it out, and it become like this. So the process is quite easy. Now this is the thing. So this one is aluminum. This one is aluminum. Then this is a laminated steel. Laminated steel. Why we want to reduce the eddy current loss? Its name is a squirrel cage of induction motor. Lepas tu we have a wound rotor type. The rotor will be totally wounded with a winding. So this one is called armature winding. Armature winding. This field we inject extra VDC or other field other voltages lah. But armature is not. Armature is the thing that if let's say we rotate the rotor, then we will collect the current or power. Ataupun we inject the power or current, then this will rotate by controlling the field. By controlling the field here. So this is the main one. For example, we connect to the 230 volt here. Is this winding? We call armature winding. We cannot connect 230 volt here. Everything will burn. Okay. So slip ring end of the wound rotor. So wound maksud dia wind kat sini. They wind, and then they bring into phase A, phase B, phase C macam ni. Okay. For example, not phase sorry. Maybe it's I don't know how to call this one. But I think this is a DC current only. So this one is the thing that we inject the current so into the winding. Then this is called armature winding. Then usually armature winding is come with the stator one. So wound rotor induction motor is used as a doubly fed wound rotor generator, which is very popular in the offshore. Why we call doubly fed? Doubly fed means maybe they have a two type of induction motor inside there, inside this one. Okay. And then what we have? Okay, synchronous motor. Stator is applied with a polyphase winding. Rotor is applied with a wound field winding. So this I think kat atas sudah ada lah. Macam induction motor, we also call as asynchronous. Asynchronous motor. AC motor, synchronous motor means the field, the north field and the south field will react with the armature winding synchronously at the same time. Apa lagi? This one I think is alternator, pilot exciter, main exciter, alternator. Okay, alternator is another type of machine. If let's say you in the beginning we talk about electrical machine, right? Electrical machine has two things. One is a static, okay. One is a rotating. Then the static one is a transformer. Rotating one can be a generator or motor. One type of generator we call alternator. If you're familiar with a car, right? our car have one alternator. It used to charge our battery, and the simplest alternator there lah. So alternator is a generator, yeah. So in our I'm not sure what is this application. If not mistaken, it's a power generator. It is a generator. So because of one of it is an alternator, another one is a main exciter, which used to synchronize the um, the field code. This one I'm not sure. This one I'm not sure. This is the things that we need to learn in our subject lah. So I think before I go into this one, I just want to tell you that maybe there's a one slide. This one code. Is it? Aha. Okay. Maybe not really. I want to tell you to bear in mind that in order to have a motion of rotation or electricity, the one thing is we need to know is it must have a two reaction, which means, for example, this is north, this is south. If let's say I want this to rotate like to this direction, so what I need to do is I put north here, so that I can push this thing to here. This is one possibility. Another possibility is I put a magnet here, whereby this is south, so that it can pull from here. So there's a second possibility. This is the interaction. Usually, this one is rotating part. This is stator part. So in order to make the rotor rotate, what we need to do is we need to use the north pole put near to here, or south pole put near to here, so that it can rotate like this. So when it rotates in this direction, north, south, what we need to do is, let's say we want this magnet to rotate in this way, we need to put a south, or we need to put a north here, so that it can push or attract like this. So same as well. Now we want to make this thing inside the motor, okay, so that it can interact like this. So the thumb of rule is we must have two fields. One is a rotor field, we call excitation field. Another one is an armature winding pair field. Okay, stator field. One is a rotor field. One is a stator field. Okay, so rotor field is come from the rotor part lah. Stator field is come from stator part, and then stator part is always the winding is called armature winding lah. So for the permanent magnet, stator is applied with the polyphase winding. Stator lah, it can be one phase, two phase, or three phase. Rotor has a permanent magnet, especially like the neodymium ferrum boron, strontium cobalt, ferrite, to create a rotor magnetic field. So for example, in go back to this one. Okay. So just now you saw the video, right? One field is created here. Another field is come from stator part. So we have two fields. One is a rotor field, one is stator field. To make the motor rotate. Same as well. Rotor field, stator field. This one is stator field, rotor field. Okay. Another one. This is a rotor field. This is a stator field. Okay. So same as well. For permanent magnet, the rotor with it has a permanent magnet. They act as a rotor. For stator, it has an armature winding. So sometimes it's called as a permanent brushless synchronous motor. Why we call brushless? Okay. This one is called brush, not brushless. With brush. Okay, with brush. This is brushless. Brushless. But induction motor, we seldom use brushless. we seldom call it as a brushless because we understand it is no brush, seldom got brush. This is a brush. Okay, so this one is brushless because the rotor itself already has a permanent magnet. We don't need to use a brush. And then so we call brushless synchronous motor. Synchronous, why I call it synchronous? Because the field need to always synchronously, which means we need to know where is the north pole, and then we will know where is our south pole or north pole to be used in the stator. For example, we need to know where is the north pole of the rotor here. Where is the north pole of the rotor here? So that we will know where should we put the stator as a north and the south pole. It will synchronously, not synchronous. And then it can be operated by AC motor or DC motor. Actually, both of them as overall is AC motor. The current drawing from the wire here is AC, but the operation can be AC or DC. Operation here can be AC or DC in terms of, if let's say we want to run this motor by injecting the current, we can either inject AC or we can inject DC to run it. If let's say we inject DC to run it, we call it as a PM brushless DC motor. If let's say we inject AC to run it, we call it as a PM brushless AC motor. That's it. But as overall, it is AC motor. No matter we inject DC or AC, it is AC motor. Why we call DC as an AC motor? Because the DC here, we are using the converter. We inject the DC, and then they use this DC to control become AC to run this. Eventually, it's still AC. So require power electronic converter and position sensor to operate. This is the bad thing. Disadvantages here. We need to know where is the north pole. As I told you, we need to know where is the north pole of the rotor. We need to know where is the north pole of the rotor. Baru kita tahu what current we need to put inside the stator. So highly efficient and good dynamic response. Dynamic response means, if let's say we want to speed up the motor, then it can react very fast. We want to slow down the motor, it can react very fast. This is called dynamic response. Sophisticated control algorithm, for example, vector control, flux absorber, Kalman filter, direct torque, space vector, zero crossing back EMF control. This is a control method on how to drive the PM motor. PM motor. Okay, so this is one type of a PM motor. This is another type of PM motor. This type of PM motor we usually use in Prius. We call it as an interior permanent magnet motor. Interior, okay, permanent magnet motor. Okay, then some of the application. Another type is a switch reluctant motor. Switch reluctant is actually there's no permanent magnet. We need to know where is the rotor, so that we can switch on the for example this winding, and then to make it become a north pole or south pole, so that it will be attract like this. Then for example, if let's say I put a north pole, so that it attract like this. So I need to switch on here, and then I turn off here. When it comes to let's say this position, I want to attract it by using south, so I switch off this one, I switch on this one, then it will attract it to be here. So this is called the switch reluctant motor. It can be singly excited or doubly salient. Singly excited means we excite the coil in one coil. Doubly salient means salient I don't know how to explain here. Then only stator carries the winding, and then no winding or permanent magnet on the rotor structure. So this is only a steel, no permanent magnet. In here, yes, we have a permanent magnet. This is the permanent magnet. This is the permanent magnet. This is the permanent magnet. Okay. This one no permanent magnet at all. Only steel. Only steel. Rotor is made of a laminated steel iron, simple, robust, with a high pressure environment. but very low efficiency. So it can be how to say. This one is called Darby salient. Darby salient. I don't know, this one I need to check what is the meaning of the Darby salient. Salient is something like this chakok. So the motor can be designed like this, and then yeah, the SRM, switch rudder stepper motor. Stepping motor is like the servo motor. It has a stepping like tuck 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 like this one, tuck 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 tuck. And then permanent magnet stepper motor. So similar to SRM, switch rudder motor, but the rotor now has a permanent magnet. So we have a north and a south pole. Just now, SRM tak ada permanent, tak ada magnet, hanya steel saja. This is only steel. So and then hybrid stepper motor. Hybrid means campuran. The reduction and permanent magnet, which means maybe one part got permanent magnet, the other part has no permanent magnet. This is hybrid, but it's a stepper motor. For example, here, this one no permanent magnet, this one with permanent magnet, and then the end is no permanent magnet. Stepper motor. So schematic view of the hybrid stepper motor, two-step rotor with axially directed permanent magnet. Okay, this one don't to I just study Just want to tell you that we have a hybrid motor. Finish. Okay. So finish this one, the basic. Okay, now we go to basic concept and structure of electrical machine. Just now is just a introduction, what type of motor we have. So if let's say I want you to absorb everything for one day of all the motors, it is impossible. It is impossible. At least you come across, yeah, you learned about, you know about what is you listen before, what is the stepper motor, what is the switch reluctant motor. In this subject, we focus on permanent magnet motor. Even in your mini project will be permanent magnet motor. So basic concept and the structure of electrical machine. Generally, we will consider several motor concepts and terminology. So before we start to learn on motor design, we need to know the terminology, the name of the motor parts, and also we need to know the concept before we can go inside. So we need to understand in order to effectively design the electrical motor. Many are very applicable to almost all types of electrical machine. So use motor to do work. When we use motor to do work, because motor is actually generate the movement, right? Kinematics. So rotating movement of the most motors the output is the torque. So if let's say we are electrical engineer in the electrical machine, we don't usually use power as explanation, but we use torque. Power is just like for those who are not engineering very well so for those who from civil engineer, they don't understand what is torque, but they understand what is power. For example, we talk about, this aircon got 1 horsepower. My aircon is 1 horsepower. I put 1.5 horsepower at the living room. In my room is 1 horsepower. This okay. But if let's say we say that, my aircon is 0.5 Newton meter torque, then dia akan kena stun lah. They will just stagnant there. What is that? If let's say I'm the promoter, then I'm doing in a sand queue or sand hang, and then an electrical shop. Then I go to tell my customer, like, this aircon got 0.5 Newton meter of torque. They don't know anything. Okay, but we as an engineer, especially in the machine design, electrical machine design, we seldom use power, but we use torque. The torque is called electromagnetic torque. Actually, the torque is relationship with the power, torque times T omega, which means if let's say there's a shaft here, let's say this is a shaft here, we rotate the shaft, and then the output power, if I measure, it is 300 watt. Okay, then if converted to the electromagnetic torque, maybe the rotation is about 500 RPM. So the electromagnetic torque is about maybe 0.2, let's say 0.2. This is what we need to understand. Torque cannot be feel. We cannot feel the torque. Sorry, we cannot measure by hand the torque. Okay, so we need to use a specific measurement tools to measure the torque. But power, yes, maybe we still can measure the power. Linear movement, linear motor output is the thrust, Newton. So linear movement. Material used for electrical motors. So need to consider the electrical, magnetic, and mechanical constraint. So electrical, what is the current? And then magnetic is like the so-called flux density they generated. Mechanical is like how we construct the motor. So this is the things that we need to consider for the electrical motor design, electrical machine design. Electrical constraints such as core losses, copper losses, non-linearity of steel iron, inductances, and increasing resistance due to the higher operating temperature. Everything here we will be considered in electrical machine design. Then magnetic constraints such as armature reaction. Armature reaction is the reaction due to the armature. If you still remember, this is a rotor field. This is a stator field. Rotor is a Newton, north and south pole. Let's say this is stator. This is so this will be attract like this. Sorry, it will be attract like this. Okay, for example, I put the north, the south here, north here. So this is a stator field. So that I want to attract it, it becomes this is attract, right? So this will move to the top lah. Okay, and then what is armature reaction? Armature reaction is the reaction due to armature winding. Reaction due to armature winding. So where is armature? So armature is here, with coil here. Okay, if let's say we inject current, then we will get the north and south pole. If let's say we do not inject, then nothing here. Okay, so now we want to see, if let's say I inject the current, what will happen in here? So this is so-called armature reaction. Then ion saturation, clogging torque, irreversible demagnetization of the magnet. Ion saturation is like the steel bar. Okay, if let's say we know that V, the saturation is a 1.5 Tesla. Okay, if let's say we inject 1 Tesla, so we may receive 1 Tesla. If let's say we inject 1.5 Tesla, it may give us 1.5 Tesla. But if let's say we inject 1.8 Tesla, maybe here we're about 1.6 Tesla. Why? Because the steel cannot give us the more bandwidth for the flux flowing through, which is already saturated, the so-called ion saturation. So which means if let's say when it cannot flow through here, then we will have losses. Okay, then clogging torque is the unwanted torque, the torque that we don't want. When we try to, for example, if let's say we put the permanent magnet here, and then we know that the north pole and south pole will attract. Ataupun we put north pole here, south pole here. So north and north will push. So this is the energy they have itself, which is we do not do anything. We do nothing. We are not giving current. We are not giving pushing, but they push themselves. When it comes to the system, it will create a torque that we don't want, which is called unwanted torque, clogging torque. Later on, when we go to the motor design, then we know. Then irreversible demagnetization. If let's say today we magnetize here, become north and south pole. Suddenly we put too much magnetic field onto this field in the direction of a here. Then this will push all the magnetic field in the other way around. Then it become demagnetized. When it demagnetized, it may also become irreversible. Magnetized, if let's say reversible, maksudnya if let's say we give the so-called, let's say Sn. If let's say we know that the current is flowing out, the flux is flowing out. If let's say we give the field flowing inside, then until when we release it, we cannot get back, let's say 1.6 Tesla. Let's say original is 1.6 Tesla. Then we impose 2 Tesla for the opposite one. And then after that we release it. Then we found that the recorded Tesla it become 1.2 Tesla, for example. This one is so-called demagnetized. The block itself already hilang kemagnetan dia. It's irreversible, cannot be reversed back. Okay, so I think let me go to the last one. Mechanical constraints such as a minimum maximum limit of operating temperature for various components used in the motor. Okay, for example, magnet can be demagnetized when it reaches 180 degrees. So this is the constraint. This is constraint. So that when we run the permanent magnet motor, we cannot run it too hot. If it is too hot, then it will be demagnetized. When demagnetized, there's no magnet at all. Okay, so for various components used in the motor, space, envelope cooling system, noise, vibration, maximum speed limit, unbalanced magnetic pull. I will tell you magnetic pull when come to the almost the end. When come to the appropriate place, then due to the rotor eccentricity. Eccentricity means the shaft already dia punya bearing sudah rosak. For example, this is the shaft. Okay, this is the bearing. Okay, this is the bearing. If the bearing it become deformed, become like this, if the bearing dia sengit, it deform, it deform. Okay, when this one rotate, then it will become bergetar, will move around like this. Sometimes you move there, sometimes move here, sometimes move there, sometimes move here. Then it becomes not eccentric. So when we see from here, okay, the rotor shaft, if let's say normal range of moving like this, sometimes it will move to here. Sometimes it will move to here. So this is called eccentricity. It will move like going down or going up or going this, going there, like this. Also, this is eccentric. So we stop here for 10 minutes. 4 o'clock we come back again, yeah.